So in the first part we saw feature selection, in which we, from a set of features, selected a subset that was more useful for our purpose. But there is a different approach, which is feature extraction. We start with a set of features and we create a new set of features or new features from the original data. We are going to see some ways of doing feature extraction, which is we are not keeping the same features as we had originally, but we are keeping some transformation of the features. And one very used approach is this principal component analysis that is often used when we want to reduce the number of features that we're going to use. So this can help us combine original features into a new set of features. I'm also going to talk about self-organizing maps, which are a convenient way of visualizing in 2 dimensions data that has n dimensions. And it's also a way of transforming these features in a sense. And then I'm going to give you an example of this feature extraction and self-organizing map to see a more practical example of an application of these techniques. So the idea of feature extraction is to extract useful features from the original data. This can be done, it's often done when we have unstructured data, so we need to extract some features. One example, you saw an example of this in your first assignment, where you had those 4 features for the banknotes. These were extracted from the images, were statistics computed from the original images. So this often happens when you are dealing with image data. You need to extract some features in order to work with those images. Or if you're using, say, text, words in text, or sound frequencies or something like that, generally for that kind of data where you don't have a well-structured number of features, you need to extract these feature values from the unstructured data. Or you can transform your original features into a set of features that is more useful. There are many specific solutions in specific domains, but we're going to see one very general approach, which is this principal component analysis that we can use in general for transforming sets of features. So the idea here is that we start with a set of continuous valued features in n dimensions, and we want to transform, we want to find the rotation of those, of that cloud of points, such that the first vector will align with the longest spread or the greatest dispersion of points, so the direction where the points are more spread out. The second vector is perpendicular to the first one and is aligned with the most of the remaining variance or the remaining spread, and so on. So we are going to align the shape of our cloud of points with the vectors in this new base. And then we can reduce dimensionality by keeping the first k vectors. So basically, principal component analysis allows us to reduce the dimension of our data set, preserving as much as possible of the variance after this reduction. So let's start with an example. Suppose that we have this data set here. This has the points are spread out in a diagonal, and we want to reduce from 3 dimensions to 2 dimensions, but keeping as much of this dispersion as possible. You can see that if we simply project this into any of these axes, we lose part of the variance because the points are spread out in the diagonal. So any projection in any of the 3 axes will compress the spread of the points and make them closer together. So we want to find the best set of vectors to do this projection here. And I'm going to explain briefly how we can do principal component analysis. In practice, you can use the PCA class in scikit-learn. But the idea is that we're going to find the central point of all our data cloud, of all our examples, And now we're going to build this scatter matrix. The scatter matrix is equivalent to the covariance matrix, but without normalization. So if we divide the scatter matrix by the number of points, we have the covariance matrix. And this is a matrix that has, it's a square matrix in which the size is the number of dimensions in our data. So in this case, it will be a matrix that is 3 by 3. And each entry in this matrix gives us the covariance between on the data that we have between the two features there. So we basically are computing a matrix that describes how our data is stretched or spread out in its space. And now we're going to find the eigenvectors for this scatter matrix. The eigenvectors for a matrix are the vectors that we can use to multiply a matrix and obtain some vector that has the same direction as the eigenvector. So basically, these are the vectors where the matrix stretches, or where the matrix, when we use it to transform the vector, simply stretches to one direction. And we're finding, so when we're finding the eigenvectors, you can imagine that we're finding the vectors where the matrix is describing the spread of the point. So this is basically what we can do. We can do it like this. We find the mean point for all the data that we have, so the central point of this class of points here. Then we compute the scatter matrix by going for each of the points and doing this outer product between the vectors after centering. And so we have this matrix that has a shape of 3 by 3. This is the scatter matrix that we compute. Now we can use this method from NumPy to get from the linear algebra module to compute the eigenvectors and the eigenvalues. And we have here the 3 eigenvalues. These are give us the dimension of the vector, so to speak, or tells us which direction has the greatest variance, the second greatest, and so on. And these are the vectors that we obtained, the eigenvectors for this matrix. So we know that we can project everything into one dimension, keeping the most variance possible if we use this first eigenvector. So this is the direction where the points are most spread out. Then perpendicular to that, we have this third one here, which tells us where the remaining of the variance is largest, and so on. So we can use these two, the first one and the last one, to reduce our data from 3 dimensions to 2, while keeping as much variance as possible in our data set. So basically these are the vectors here. Notice this one is aligned with this diagonal where the points are spread out. The other two are perpendicular and have the remaining variance there. So if we choose the first and the third one here, we transform our data into that by projecting into those two directions, and then plot, and this will be the result. So the first eigenvector is where we have the largest range of values here. This was the vector that corresponded to this diagonal here, so this vector. It has the largest spread of values. And then one of the other two has the remaining largest variance, and we use that as the y vector here. So this projection preserves as much spread as possible on our data set by doing this rotation and projection with from the original 3 dimensions to 2 dimensions. So basically, with principal component analysis, we compute new features. Notice that the features that we have here are not identical to the original ones, because we are using combinations of the original features when we do this rotation. And we compute these new features, and we reduce the number of features while keeping as much as the variance as possible. So if you want to do this with scikit-learn, you can, from this decomposition model, you can import the PCA class, and you just tell how many components you fit with the data, and then you can transform the data into the new data after this rotation and projection. So you determine how many features you want to keep, and this will transform the original features and will extract this number of features that's specified. Note that this is not the same as feature selection, because the final features that you have here are do not correspond to any individual feature in the original data, because they are a transformation of all the features at the same time. Okay. So let's see one way of representing multidimensional data in 2 dimensions, or to map multidimensional data in 2 dimensions, which is using a self-organizing map. You can imagine the self-organizing map as a special kind of artificial neural network, where you have each of your neurons has an input vector that has the same dimension as your data has. So each input into the neurons corresponds to the value of one feature of your data. But your neurons are arranged in a 2-dimensional matrix, where each neuron has some neighbors in this matrix, so like a grid of neurons, where each neuron then has the weights pointing to the space of your data. And we have 2 distance measures here. We can use the coefficients of the inputs for the neuron as a position in our data space to determine which neuron is closer to any data point. But we also have the position of the neuron in the grid. So we know that one neuron has neighbors in the grid. And now the training method for a self-organizing map is to start all our neurons with random small coefficients. So imagine that we are spreading them in the space of our data in in the center of that space at random. And then for each training example, we present one example to the network. We find the neuron that is closest to that example in the space of our data, and now we adjust the coefficients of that neuron so that it's closer to the example we presented. But we also change the coefficients of the neurons nearby in the grid to also move in the same direction. So we can imagine that we have 2 different spaces, the grid and the space of our example. When we present an example, we find the neuron that is closest to that example, and we pull it a bit towards that example. But we are also going to move the neurons that are nearby in this 2-dimensional grid, and they will also shift towards the example. So you can imagine that what we are doing is we are stretching and bending this rubber sheet with our neurons to try to touch as well as possible all the points in our training set. But we still keep the rubber sheet in the same topology. So we can then take it out and we can just plot the grid of the neurons representing our data. So let's see a simple example here. We have color space in 3 dimensions, red, green, and blue. So each color we can represent as a value, as a set of 3 numbers between 0 and 1. And we can have a data set here with some colors and some names that we can assign to each color. For example, black is all zeros, blue is 0 red, 0 green, 1 blue, and so forth. And now we can use a self-organizing map module. So this is not part of scikit-learn, but it's easy to find. There are many implementations of this in Python. So in this case, this is mini-tom, which initializes the network with the dimensions that we give it, and then sets up the neurons with random weights and trains a number of batches with our data set. So we can do this easily by creating the matrix with 20 by 30 neurons in our grid. We have a depth of 3 because each neuron will have 3 coefficients corresponding to red, green, and blue in the space of the colors. We specify the learning rate and the neighborhoods in the grid that it's going to use to pull neighbor neurons. We initialize the weights, and then we train with 10,000 batches by passing all these colors through the network 10,000 times. Okay. And now we can represent the results and plot the names of the colors in the location of the neuron that is closest to each color. So this is the result here. The grid with 30 by 20 neurons that we have here is two-dimensional. But each neuron has a three-dimensional set of coefficients that points to some point in the color space. But since the training, when we pull one neuron, we also pull the neighbors during training. This means that neurons that are close together in the neuron grid will have similar colors. So the colors are all spread out in a way that makes contiguous values have similar colors. And also then we can place the different names of the colors into the region of this grid corresponding to the closest neuron to that particular color. So we can project colors from 3 dimensions to 2 dimensions in this diagram here and know where each of them will be placed in 2 dimensions. Okay? So this is one way. Self-organizing maps is a useful way of representing high-dimensional data in 2 dimensions too, while preserving some this topology, this relation between similar points.
So the inputs for the neurons are the values, right? The RGB.
Yes, for training, it's this set of colors. So actually, the training set was this set of colors that we have here. Each color has one set of coordinates in 3-dimensional space. Each neuron also has a set of coordinates in 3-dimensional space. So when you present one color, you find the neuron that is closest to that color in 3-dimensional space. And you move that neuron closer to the color. So the example pulls the neuron towards that point in the 3-dimensional space. But you also do the same thing for the neighboring neurons. So this means that as the neurons spread out in the color space, they will tend to keep that topology defined by the grid because the neighbors are also pulled when you find the closest one. So this will start all jumbled up because you start with random locations, but as you start training and spreading this membrane, it will smoothen out and order itself according to how the data points are spread, but also according to that topology of the grid. So this means that these neurons here, for example, the neuron that is closest to red, its neighbors were also pulled towards red. But this one at yellow was also pulling these ones here. So you have neurons here that are orange because they fall between yellow and red. You see, we are keeping the neurons together in this grid in 2 dimensions, but we are also adjusting their coefficients in the 3-dimensional color space. So this is how you end up with the projection from 3 dimensions to 2 dimensions. Okay, let's see a specific example where we put these things together: feature extraction and then self-organizing maps. You have in this site here, Gapminder, you have data on indicators that change across the years for different countries. In this case, we're going to use gross domestic product per capita, life expectancy, infant mortality, and employment of people over 15 years. Each of these indicators is provided in an Excel sheet that has in each line one country, and then each column corresponds to a year, and we have lots of values for the different countries. We don't have values for every year for every country, so there are missing values here, and we don't know how many values we have for each country. And we are using these 4 indicators. So you see, the first problem here is that basically we have something like this. For example, for Portugal, we have estimated life expectancy here, then measured values here. We have mortality, infant mortality rate, gross domestic product, and employment rate for over 15. So you see, different indicators have different numbers of years for which we have values, and also for different countries we may not have the same year. So starting from this data, it will be hard to do anything with it in this shape. So the first step, we need to do feature extraction and try to organize some set of descriptors for each country so that we can have anything in a neat table. And this would be the first step that we take. So, feature extraction. There are many different ways you can do this, but usually it involves thinking a bit about how you're going to describe the data. In this case, we can compute a polynomial regression for each series. So each of these series, for example, red here, which is infant mortality, life expectancy in green, and so on, we can compute a polynomial regression for these points. If we describe each series with a polynomial with 4 coefficients, so cubic polynomial, we will have for these cubic polynomials, degree 3 with 4 coefficients, we have 4 indicators. This will give us a total of 16 features. And now every country will have these 16 features, which are the 4 coefficients for each of the polynomials for each of the 4 indicators that we're using. So this would be one way of converting this unstructured data or data that is very difficult to work with raw, and converting it into something that we can use that is more structured. So in this case, this is the set of all the regressions for all the countries in gray, and here we see Portugal. So this red line here is infant mortality, this is the unemployment, the life expectancy in green, and GDP here in blue. The curves now are a bit strange because outside the range of the data they are just extrapolating. We don't know what values they should have, but what matters now is that each country has these 16 coefficients for the 4 polynomials. So now we can build a table where for each country we have a descriptor with 16 dimensions. Of course, now we have a problem because with 16 dimensions it's very hard to visualize the relations between countries, but we can now compute, after extracting this, we can now train a self-organizing map and project everything into 2 dimensions. The same thing we did with the colors, but instead of going from 3 to 2 dimensions, we're going from 16 to 2 dimensions, but the idea is the same. So we create a self-organizing map with 30 by 45 neurons. We have this number of features, the 16 features. Our descriptors are descriptors for all the countries, and then we train the self-organizing map. Then we have these names of countries to place on the graph, and we create the figure. And we can also use, in this case, so in this case here, I used the actual neuron coordinates for creating this bitmap, because the neuron coordinates are the red, green, and blue components, and when we use that as an image, it will display the different colors. In this case, now I'm going to use a range of colors from black to white, in this way, where we are representing how stretched the self-organizing map is, so the distance between neurons in the data space. And now you can see how the countries are distributed here. After we project everything using SOM, we have Portugal here, somewhere between Sweden and Kazakhstan. I don't know exactly what that means, but that's where it ends up. And then we have Syria here, Saudi Arabia, Bolivia, Egypt, and so on, Angola over here on this side. And notice Qatar here. Qatar is very far from the rest, and the SOM is very stretched here, because probably a small country, very rich in oil, with a very strange pattern of development over the years, so it ended up with some coefficients for those polynomials that are very different from the rest. But in this way we can represent the distribution of countries, and basically what we did here was we went from data set like this, so we have 4 Excel sheets with missing values and different number of values per country. We extracted features with the polynomials. We have each country now described in 16 dimensions with a vector of 16 features, and now we can use self-organizing maps to visualize how they are spread out. So this is just an example of how we can put these things together in practice to go from some unstructured data into something that we can try to use to understand the relations between the data. So that's all for today. What we saw here was the idea of feature extraction. This is just a brief set of examples. but the basic idea, the important idea, is that you can start with features that are not very nice, either have a structured data set and want to convert the features into something else, or have something unstructured for which you need first to have some sorted out features that you can use. So you can extract features from the data. We saw principal component analysis as one way of reducing dimensionality, which has the advantage, if you use this one, you are preserving as much as the dispersion, as much of the variance as possible in your data. And we also saw self-organizing maps as another way of projecting things into 2 dimensions by training this membrane of neurons to fit the shape of your data. And we saw this example where you can start with unstructured data or very messy data, try to extract some features, and then use those. The big difference between feature selection and feature extraction is when you do feature selection, you end up with a subset of the same features you started with. You're just throwing some of them away. With feature extraction, you start with features that do not correspond directly to any of the original ones. So you're transforming your data into something that is more useful. So you can read more about PCA, scikit-learn. If you want, you can look at self-organizing maps here in Wikipedia. But this is just I'm not including self-organizing maps as an important part of the subject matter here. It's just an example of this kind of operations of projecting, reducing dimensionality, feature extraction, and so on. So, questions?